We'll get going. So welcome everyone and good afternoon. My name is McKenna Sellers. I'm the Executive Director for the Montana Renewable Energy Association. And I'm glad you all are joining us here for the November Exploring Energy series. The topic du jour is geothermal exchange systems, and we're very excited to have Jim and Gil as our guest speakers today. So a little bit more about the Exploring Energy series. This is a monthly lunchtime presentation where we cover energy issues impacting Montana and beyond. We typically hold these on the first Wednesday of the month. This is an out of cycle presentation, but we'll be back in cycle with the first Wednesday in December to close out the year in 2024. And we hold these at 12 o'clock Mountain Time to explore renewable energy technology, the latest trends in energy development, and connect with experts working on the future of our energy system. We have a really excellent archive of past presentations on the MREA YouTube channel. You can find that through our website, which I just put in the chat, or you can go direct to our YouTube page to the Exploring Energy playlist, but a ton of excellent resources can be found there. So a few housekeeping items. If you could keep yourself muted during this presentation, that would be excellent. There will be an opportunity for Q&A at the end of the presentation. If you have questions that you want to keep top of mind, you can put them directly in the chat at any time. And if for whatever reason we're not able to get to your question, you should send us an email at info@montanarenewables.org. We'll be sure to connect you to the right people. And this session is being recorded and will be available later this week to everyone who registered. Is my sound quality still coming in? It looks like my video froze.
Yeah, your audio is good.
Okay, so don't mind the ghostly face. I'm still here. A little bit on membership. So MREA is a 501c3 nonprofit. We're a member-based organization that focuses on advancing renewables in the state of Montana through community education, such as the Exploring Energy series, which we hold monthly, through policy and advocacy work, and also through our industry engagement, thinking about the next generation of the workforce and building a sustainable workforce in Montana. If you like the work that we're doing and you want to be involved, we encourage you to become a member of MREA or consider supporting MREA with your year-end giving plan in 2025. And if you're a QR code type of person, we have the QR code for how to join or donate to the Montana Renewable Energy Association right here. So with that, I am very grateful to introduce our guest speakers today, Jim Speyer and Dr. Gil Rodgers. I'll start out with Dr. Rodgers' bio first. So Dr. Gil Rodgers is a senior advisor with StoneTurn. He has 40 years experience in the energy industry, holding senior positions in both the private sector and US federal government. He specializes in energy strategies, carbon management, asset investments, providing technical, economic, and regulatory guidance to investors and senior management. As a leading partner in the Minerva Action Group, he promotes climate science education through hands-on experiences for students. His expertise spans advanced quantitative methods, emerging energy technologies, and effective communication with top-level executives and regulatory bodies. His focus is particularly on applications of underground geothermal heat pump and energy systems. And now Jim Speyer, who is also a senior advisor at StoneTurn, specializes in strategic analysis of energy and environmental issues across coal, gas, nuclear, and renewable energy industries. He's held key positions, including on President Carter's White House energy staff, as the Director of Coal and Utility Policy at the US Department of Energy, and as the Director of Energy Policy at the EPA. And with over 4 decades of consulting experience, he advises on strategic planning, mergers, and environmental compliance, while also assisting in litigation and testifying before various regulatory bodies. Jim serves on the boards of Energy Conservation Works in Jackson and the Jackson Hole Center for Global Affairs in Wyoming. So thank you both, Jim and Gil, for joining us, and the floor is yours.
Okay, I'm trying to log into my slides.
Gil, can you do what you did last time?
I think I can do it here. No, I did it a little different way. Okay, well, McKenna, thanks so much, and it's really a pleasure to be here and with Jim to talk a little bit about geothermal heat pump systems and its applicability. And you gave a nice summary of my background, and yes, I've been in energy since the 70s, late 70s. And my background is in engineering, particularly electrical engineering and economics. And I've had quite a bit of work recently in some of the new renewable technologies, such as solar. And then I'm very excited about the geothermal systems because it's another very important aspect of renewable energy that's often left out, I think. So I think talking about it is very, very helpful. Jim, did you want to say anything more about your own background?
The only thing I want to add about the introduction by McKenna is I've had a lifelong connection with Montana. Starting in the mid 50s, we visited Western Montana. And since the mid 60s, our family's had a house on Lake McDonald in Glacier National Park. So I go there practically every year. So with that, Gil, why don't you just go into...
Okay. And we have a relatively short presentation because we find that it's usually most helpful to have Q&A and discussion. So this is a summary slide of geothermal energy systems. And without getting too much into the excruciating details of this, let me just say a couple of comments about it. You can see over on the left, the blue loop. That's the underground loops or boreholes that a geothermal system has. And you can see that these are, they're typically with water and also ethylene glycol or some type of an antifreeze. And that's basically pumped into a set of boreholes at that site. Then there's really two steps in the heat exchange. One is to take the energy that's in that water, that pumped water, which typically is constant at 50, maybe 55, 60 degrees. And then using a refrigerant to capture or to absorb that energy, and that's starting to be the like the purple lines that's moving in toward the right. Then, and if you've had a little bit of physics, you know that if you compress that, if you compress that fluid, that refrigerant, okay, I'll say a little bit of what those are. Then what happens is the temperature goes up. In other words, there's an exchange of energy from the blue loop, from the underground system, into a system that's over on the right side of the diagram, which is another loop that's for the buildings and the end users of it. And so the purple line is showing that the refrigerant is compressed, the temperature goes up, and then that's sent over to heat pumps that are in the individual buildings. And then the energy that's in that refrigerant then is condensed and is put into the room. And then there's a circulation system, and then the whole system flows back. Then it returns back, and now I'm down at the bottom of the picture on the yellow sort of line there, and you see there's an expansion valve. So the pressure goes down, temperature goes down, and then the cycle is repeated. So it's very similar to what you have in your refrigerator. So a lot of people think, oh, this is sort of really Star Wars and stuff, and it's not. It's simply a refrigeration cycle that you have, that everybody has in their in their home.
But
Very
this,
common lesions.
it provides both heating and cooling.
Now, the whole system, right, Jim? The whole system, then I've explained it kind of for heating. Now, the whole thing can be reversed. So all those little arrows can go in the opposite direction. So it can take energy out or heat, say, out of the buildings, out of the rooms, and then reverse the whole flow and put that heat and that energy back in the ground again. So it's the whole system is a reversible system. And that becomes very important for understanding these geothermal energy systems, because there's the balance between the cooling and the heating. And it's very important that that balance is maintained. So it's a bi-directional system. Now, let me just say, and you can probably add to this, but what I have found, I was out at the Mountain Towns event just a couple weeks ago in Jackson, and had a chance to talk to a lot of people. And one of the things that I found in going to that, which was very exciting for me, was how interested and relevant geothermal energy and other renewable energy is in Colorado, but in the West and in Montana. And there's a great deal of interest in grid decarbonization, bring the carbon levels down. This is a picture, a slide that I really kind of modified a little bit, but I took from one of the presentations on geothermal that was at this event, which was, I thought, a very good presentation. And first of all, it on the left is just mentioning some of the things that makes it so relevant for Montana. One is the geology itself, the rock structure. Now, so you're depending on the energy that's been stored in the earth, millions of years ago, as the Tetons and the Rockies were formed, that has captured energy from the sun and is stored in rock. So, and I did a couple cases, I'll come to them in a minute, about the actual applications of geothermal in that area. So Montana and other Western states, and of the people I talked to, it just was universally well understood, well accepted. And so it seemed like this presentation and talking about this was very relevant. The other the thing that's very good is that the geothermal systems are utilizing the ambient temperatures that's in the rock structures and in the aquifers, the underground systems, which are very stable, unlike the temperature fluctuations that you get in the air. So, we're getting into the winter season now with cold temperatures, and we have the variations between the warm or hot, even summers. We've had some very extreme high temperatures in other parts of the country, and then the extreme lows in the winter period. So one of the things that's good about geothermal is that it's a very stable system, even in these extreme variations in the weather patterns. And then the mountain towns also, I think, have a lot of very special, unique challenges. A couple of things, of course, is just the altitude, the atmosphere, the temperatures of the air. Another is just the systems itself, the electric systems and power systems and all. So there's unique characteristics that make it particularly relevant, I think, these systems for this part of the country. I'm in Boston and finding a lot of applications for geothermal around here, but having lived in California and been on the West some, just see overwhelming interest and potential in Montana and other states. Now, the other thing, we're going to focus mainly on heating and cooling, but there's also electricity. And there is a whole technology of producing electricity through geothermal. Now we're talking about heating and cooling of buildings and rooms primarily, but there's also another whole part of it, and that's another very exciting and dynamic area because there's a lot of effort for electrification of buildings, and of course with electric vehicles now becoming very important and being part of the demand and the demand requirements for energy, that's becoming also very, very, very important. The electric demand that's growing, particularly for electric vehicles. And I've done quite a bit of work on the technology for electric vehicles and batteries. And that's going to be a big growing area as well. And then the one thing that I thought was very interesting, and again, I'm borrowing this from one of the presentations that I saw at Jackson, is this Falcon curve, which I thought was very interesting, and that's on the right side. And you can see for typical, basically it's a graph of the energy demand, and then as a function of time, of months of the year. And you can see how the red line at the top, that would be for a typical baseboard heating system, you know, where you're using electricity to warm up the buildings or the schools or offices as a function of time. And it's very sharp. See, it's a very peaked curve. Now, one of the things that now I'm going to use this term quite a bit is the coefficient of performance, or COP. And I won't get into too much of the detail, but it's basically the efficiency of delivering energy. And you can see for an electric baseboard that they think that the COP is like 1. And then if you look at these alternatives, and one of the main alternatives to a geothermal heat pump system is an air-to-air heat pump system. And that's the blue line, and that looks better. In other words, it's not as peaky, it's more flat. And that has an average of, say, around 2, COP of 2. So it's twice as efficient as the electric baseboard. But then you look at the next line, which is the green, and that's a ground source heat pump system. And again, it's using the technology that I just mentioned. And we'll see some of the examples of that, but the coefficient of performance, the COP, is maybe twice as good as an air source heat pump system. And then one of the things that is important in these geothermal systems is how interconnected they are. And you think that that's sort of a minor point. It's not. It's a very important part of these systems to interconnect the different buildings. So I call this, and you can see it in the title here, a district geothermal energy system versus just a geothermal energy system. And by district, I mean multiple buildings, and that they're connected together. And why is that important? Well, it's important because like in a school, in a campus, you can have different temperatures, you can have different ambient conditions in different buildings. And with a district geothermal system, in addition to this heat pump system and taking energy out of the earth, the district geothermal systems interconnect the buildings. So they can take energy that's in one building, say that's warmer at certain times of the year, and use it to warm up other buildings. So it has a much more efficiency, overall energy efficiency. And you'll see that in here on the purple line right at the bottom, its coefficient of performance is maybe 6. So it's much, much, much higher than the other alternatives. And that's why a district geothermal energy system is such an interesting thing to look at. We can, it depends on our time and your level of interest and stuff, so we can do it in the Q&A. But I've done a number of detailed studies and investigations of actual real geothermal systems. Now, there's lots of hype and there's lots of conferences and there's lots of articles written about these things. But I thought that what would be important is to actually go out and meet or talk to actual installations of these things. So to go back, to systems that have been put in 10, 15, 20 years ago, and to see actually how they've performed, and to see what are some of the big characteristics to them. What are the big underlying messages from those? Now,
Hey there, Gil. Would you like that slide up right now?
why don't we come back to it? I think, right now.
Got it.
Okay. I'll mention it later on, but
Yeah.
we do have an appendix to these slides, and it has this very detailed table of what the results were from these studies that I did at different sites. And you can see, for example, I've already mentioned this, the higher energy efficiency, the higher COPs, which can be 5, and it can be way up even higher than I showed in the prior chart. There's examples of where at certain times of the year it gets up to 12.
Yeah, Gil, you may want to go to the next slide that basically summarizes your review of the existing sources. The big thing for me is you look reduction in energy costs 30 to 70%.
Mhm.
Reduction in electricity usage 25 to 35%, and then reduction in carbon 20 to 40%.
Right.
So to me, that's kind of the bottom line.
Yeah. Everybody asks that, right? They say, oh yeah, well, we're interested in this, but what are the bottom line benefits to it? And you can see these are sort of statistics that are often asked about. How much effect does it have? And as Jim said, this slide that I have up basically summarizes that.
Right.
Let me just say a few other things. So those are sort of the big number things, but there's several other things. How it quickly goes through this. First of all, these systems have been around a long time, particularly in Europe. They've been used since the 70s. So they're not a new technology, but they're a highly successful technology over longer periods of time. The detailed case studies that I mentioned, talk about how well the systems have performed. They don't wear out. The maintenance of these systems, the operation and the maintenance of these systems holds up well over many years. The systems work in colder climates, so that whereas an air-to-air system, is more, it's getting better because the heat pumps are getting wider range, but they're still kind of more for temperatures that are more moderate temperatures, more with less of the extremes that you have, so that these are good in colder climates. They have no, and I'm exaggerating that a little bit, but there's no carbon emissions, so that in all the other systems, if you have natural gas, for example, which is often the alternative, you of course have carbon dioxide emissions. But the geothermal systems are great because there's zero on-site CO2 emissions, and therefore they're consistent with carbon reduction goals and objectives that you have in towns and cities, and of course the federal government. Now they do use some electricity though, because the motors and the pumps and the compressors that I mentioned before do take electricity. So there is some electrical use. It's not zero. And then it depends on how that electricity is produced. If it's produced from renewables, then yeah, you have zero carbon emissions. But if the grid is producing electricity using fossil fuels, then you do have some CO2 emissions. One of the things that came through very strongly when I met and actually talked to these different applications, these different schools, is that it's very important to hire a company, to have a firm, a company that has real experience in the design and the engineering and building these systems. Now, there's a lot of companies out there that talk about it, but what is important is to have a company or developer, builder of geothermal systems that actually has it and has a proven track record. Because you can, there is big examples I ran across where they didn't do that. They built a system and stuff and it failed. So that experience, that real experience is very important. We'll get back to that again in just a minute. Now there's different ways that these things are financed. And one of the issues is often what are the costs, and particularly the upfront costs involved in these systems. Now we're going to talk about a different financial model in just a minute. But if you just look at the upfront costs, they have higher capital costs, higher upfront capital costs. But now there's quite a bit of incentives for offsetting that. So in the examples we looked at, the Inflation Reduction Act, for example, the federal law has this 30% federal tax credit. Then there's also state, local, and other types of financial incentives, basically, that can offset that higher upfront capital costs. So the point of this is these points 6 and 7 is that the financial aspects of these systems is very important. And I'll talk just in a minute about a relationship that we have that has a different type of financial model. Now, when you just look at the financial returns of these and you take advantage of the Inflation Reduction Act and other state and local credits, the ROIs are like 8%. So they're very attractive and they have short payback periods. So it's important to look at these systems in terms of the overall economics of it, and then how it affects the financial returns. So it's important to look at these over not just 1 year. That's one of the things that often is a mistake, is people just look at the 1 year of these things. And really what you want to do is look over the lifetime of these systems. Let me just mention now a couple examples that you know about are I think probably some of the people here on the call are maybe even involved in it. I think one of them is in Bozeman at Montana State, and this is a map on the right of the system. This is a system under development, and I don't know if Duke Elliott's on the call, but I appreciate very much. He's one of the senior engineers at Bozeman. So some of these notes and the picture particularly was from Duke. So this is an actual system, and just get an idea, it's 264 boreholes, and the depth of the drilling is 500 to 700 feet. The system provides heating, cooling for, will be 10, I don't think it's 10 buildings today, but it's 8, but then 2 more are being added. And those will represent about 700,000 square feet of floor space for the campus, for all the buildings, the dorms, the athletic facilities, the classrooms and everything. And that's about 12% of the total campus. I'm sorry, Jim, did you say something?
No, I think it's important to note that they've only covered 10% of the building, so there is considerable potential to expand this system at Montana State University.
Yeah. It reduces carbon emissions, CO2 emissions, carbon dioxide emissions by 40%. There was data available. Duke gave me data for one of the halls, one of the schools there. Carbon reductions. Another thing that's often used is what's called the EUI, an Energy Use Index. And we had some data for that. For some of the buildings, the EUI, which is a measure of the heat, thousands of BTUs per year, annually used per year, per square foot of floor space. And for these systems, they're getting like 30 to 32. To give I just looked it up, and there are some national statistics from DOE about for medium values for U.S. schools. It can be range in the range of 100 to 130,000 BTUs per square foot. And for colleges and universities, it's even higher. It's 180. So you can see the efficiency, the much higher energy efficiency that you're getting in Bozeman for these geothermal systems than typically for schools and colleges. And apparently now that some of these buildings are interconnected, but they're studying now interconnecting more so that it becomes this point that I made earlier. It becomes more of a district energy system where the buildings work together, and that helps overall with the efficiency. But the important thing is this is Montana State University in Bozeman, so it's using the rock structures and the temperatures and everything locally in that area, and you can see how successful this is. And as it grows and is expanding to a higher percentage, 10% or 12% is a starter, but there's a long way to go. Another case study that I did just to make it very real locally was at Colorado Mesa University in Grand Junction, Colorado. And that's a picture that I got from them that shows the loops, the round circles or ellipses show the different loops. It's a big system. In comparison, they have about 1.2 million square feet of building area that's covered now, that's being heated and cooled, 16 connected buildings. So it's a district energy system. And it represents something like 70% of the campus. So it's great. I mean, for Colorado, it's a system that's been around, it's been in operation. They're getting good reductions in carbon dioxide emissions. Electricity savings are significant, almost 15 million kilowatt hours per year. Natural gas is down something on the order of $12 million of energy savings since 2008. So economically, so energy-wise and environmentally wise and financially wise, cost-wise, it's been a very attractive system. So it's, to me, it's a good example to look at, to compare to. And I know some of you visited, Colorado Mesa and had a chance to see the site. Let me just say, Jim, do you want to talk about this, or you want me to mention it?
Well, you can talk about it briefly.
Okay, just briefly, who are we? All right, so we're two guys that kind of pop up on the screen. We work with StoneTurn, which is headquartered in Boston, but it's worldwide. There's offices all over, and we have a lot of background and expertise in litigation work, market analysis. Jim and I, as you've heard, have a background in energy and environment. A lot of us worked in the government. For example, I helped set up the Department of Energy. Jim was at EPA, and we've been involved with different financial institutions. We do quite a bit of work, litigation, regulatory work, policy work, setting up ESG programs and assessments of it. And StoneTurn's been in business for 20 years. I just went to their 20-year celebration, birthday party. Now, as I got involved in this and did all this research on these different sites, I kept saying, well, who are the leading companies in it? Who are really good at this that you can talk to? And through just networking, I ran across this company called Subterra Renewables. Now, Subterra Renewables is probably the leading company in designing, installing, and operating these systems in North America, with lots of examples in the United States and in Canada. So I went out of my way really to meet Subterra, had meals with the people, got to know the technical people, got to know the company and said, oh, gee, I mean, this is probably an example. There's others, I'm sure, but an example of a very strong company in this geothermal business. And so if you look at their website, they have a lot of experience in terms of drilling, for example. They have their own drilling fleets. You know, they have 60 of these drilling machines. They've done something on the order of 500 plus projects. They have, again, 25 years plus of experience.
Yeah, but Gil, just I want to make sure people know this company, and I'm sure there's others. They have a model that they'll put up the whole amount of capital cost up front,
Right.
and actually, if they need to own and operate it and recover the capital over time. So that may be appealing to some nonprofits like the universities or some other government buildings
Mhm.
that they would not have to put up any upfront capital in order to install these systems.
Yeah, exactly. There's a different model. It's a very attractive model. So let me just, there's one more. I won't go through all of this. This is sort of just a list, an itemization of what StoneTurn does, what some of the projects are that we work on. Particularly, I think an important point is maybe the fourth one down. I don't know if you can see my arrow here, but that we look at the benefits and the costs of geothermal systems and calculate what the returns are, what the payback period is, that kind of thing, and compare it with alternatives. So if a particular site has opportunity to look at an air-to-air heat pump system or something else, or a just particular renewable site, then we do that kind of detailed benefit and cost analysis, and we've done a lot of that sort of work. I personally have done lots of these kinds of studies. I won't go through all the rest of these things.
Gil, and maybe, given we're running out of time, maybe the thing to do, McKenna, is open this up to Q&A.
All right, can I just show one more picture?
Sure.
Okay, then I'll stop. Okay. And so in just preparing for this, I tried to think about what would be some of the potential sites in Montana for these systems. And basically it's just by looking around at the website and looking at opportunities. And one would be, of course, University of Montana in Missoula that we've talked about. That we also have, of course, done all this work on Montana State and see there's still a lot of potential there. The other places would be schools, high schools, grade schools, and in looking around, there seem to be some very interesting opportunities being looked at. And then as I've talked to people, particularly at the Mountain Towns event, people said, well, yeah, but also the cities, the towns themselves of Bozeman in Missoula for government office buildings would be another very good application for this, in addition to schools and universities. And then also research labs. And I see that the Rocky Mountain Laboratories, RMI, in Hamilton would be another interesting application for it. That's just a sample of these things, but just to give an idea of what are some of the potential sites for these systems. Jim, I'll stop now because I want to leave enough time for Q&A and comments and stuff.
Great. Well, thank you both. That was an excellent presentation, and I hope in these last 20 minutes we'll end by the top of the hour, if not sooner. But I'd love to pull Gil's case study analysis that does some comparison points. But before we get to that, there were a few questions. One was on the MSU campus case study. There was, and we can actually go back to it. Question from Dave Ryan: is the energy use index metrics, were those inverted? So here, let me pause and get back to that slide.
It was
Yeah, here we are. So it shows the energy use index rating of 30 to 32 compared to 20 for conventional heating. Are those numbers flipped? It was the question.
Yeah, the real comparison that I think is important is comparing the numbers that I mentioned, the 30 to 32, with what the standards are for non geothermal systems, what the typical standards are. Okay. And there, what I mentioned is in the range of 100 to 100 and up to 180 even. So the efficiencies of the systems compared to what the standard metrics are tremendously more efficient.
Let's see, that question came from Dave Ryan. Do you have any follow-up on that, Dave, if you'd like to unmute yourself? Okay. We'll move to the next question here from Bonnie Hickey. What is the expected lifetime of geothermal exchange systems? What have you all observed? How has the industry changed? Has that lifetime expanded with technology advancements?
Yeah, no, it's a very good question. And why is this important? Okay, these systems are underground, first of all. So the piping system and everything is underground. It's not being exposed to the weather and the outside. So for the underground system, for the piping system and the bore holes and that part of it, I've seen estimates up to over 100 years. And in fact, I even saw something that was like 200 years. But let's say that the lifetime of those systems, they're almost protected totally from the weather. The other thing is the heat pumps themselves, and this is a very important point, because of some of the places that I interviewed, that have older systems using air-to-air heat pumps, that the heat pump systems actually in the rooms, in the buildings and stuff, have relatively short lifetimes, like 10 years. So I talked to one, it was a residential complex, it was a senior living complex in Boston area, and the system was about 10 years old, and they're having to replace now the heat pumps after 10 years, okay? And it's been a real chore to do it because they're often hard to get at, right? They're not easy to get at. So the lifetime for the actual heat pumps, particularly the ones that are put in the individual buildings and stuff, is a relatively short time frame. In comparison, when I asked the same question to people that have the geothermal, it's twice as long, 20 years, they said. 20 years is the typical lifetime for those heat pumps. So the length of resilience and stability of the systems is much, much greater for geothermal.
Great. And it looks like we do have Dave. Hey, Dave, on that other question about the EUI. Yeah, go ahead.
Sorry about that. Yeah, the EUIs for these colleges, the numbers in this is, these are very low numbers. And so what I was going to say is the slide says the energy use index for the ground source heated systems. The slide says that it's lower, but the EUI numbers in the slide are better for conventional heating than ground source heating. Just wanted to point that out.
Yeah. And David, the thing that I think is important is how those, like 30 and 30 to 32 or 20 even, right, is very attractive relative to the other options, right, for the schools, which are 100 or 180, like colleges, it's 186, was the number that
Right.
I got.
So the slide should say 30 to 32 compared to 180.
Could be, yes.
Yeah.
Yeah.
Okay.
Yeah, much better.
just being crabby.
Okay, thanks for pointing that out, Dave. It's helpful for us to all be learning together. Okay, another question here. If Gil or Jim, whoever wants to take this one, could you expand on those COP ratings? If COP ratings are based on the equipment, then how would a COP change given groundwater temperature? I'll get to that slide here too while you answer that question.
Jim, did you want to respond to that or not?
I think they're really saying how that system varies based on the temperature of the of the uh, of the rock you bore into. And I don't know what your experience with that is.
Yeah, I think that the COP ratings that I got from the different schools, okay, are averages over over the lifetime of those systems, right? Over the 10 years or 15 years that they've been in operation. So they're the actual historical ratings of the efficiencies of the systems, given the ambient conditions and the weather conditions that's present in that location.
Okay, another question in the chat coming in. How do geothermal systems compare to biofuel systems? Are the environmental impacts of installing geothermal outweighed by the energy efficiency, just given the equipment and the necessity to dig and have ground disturbance? And then if there are continuing maintenance access issues with having underground piping.
Yeah, okay, a lot of questions there that are good. First of all, on the last part, okay, that the ones we've talked to have very little experience or very little problems with the underground systems where they've had to dig them up or something like that. You know, it's very, very seldom that they've encountered that, you know, that those sort of problems or issues that they just haven't, you know, haven't become a problem. They're protected. The other thing too in that question, which I thought was good, is for a school, for a campus. Okay, these systems are put underground, so they'd be put under an athletic field, you know, or a soccer field, or they even in some cases are put under parking garages and parking lots, so that the disturbance, and this is an important point from a biological, from an environmental perspective, is the systems are hidden, right? They're not evident. One of the things that comes up when you talk to the people is noise. And these systems, because they're underground and not exposed, you know, have very little sound to them, very little noise to them, compared to, let's say, a air-to-air system, which they're getting quieter. I mean, I have relatives that have some at one of the systems at home, and they're pretty quiet, but they're noisy. The systems can be noisy, and that can be very annoying for people, particularly if they have, you know, a heat exchanger that's outside your window someplace. So that one of the advantages is that they're quieter systems. And also there's less disturbance, right, of the environment, because if they're put in, particularly if they're building an expansion, or if it's an athletic field, or there's like around here, there's a lot of open space around the schools, then they can be put into fields and places that don't disturb the, you know, the local beauty of that particular site. It has that plus advantage to it.
And if you'll allow it, I just think that this is a great comparison chart that you worked on. So I want to have it up while we're going through the rest of the Q&A, because these case studies are so valuable. But I think it ties also with this question coming in from Dave Carlson, talking about their house. They have their what electric baseboards that fail after 40-ish years or so, and then if an air-to-air heat pump has a 25-year guarantee, is asking more about lifetime, which could be brought to a bigger question of it's not very common for a homeowner or small residents to invest in underground geothermal heat exchange because of the cost barrier. And there's likely more to it, maybe just the work involved, that it makes a lot more sense for these district systems that can happen at a university or a school. But could you speak to the threshold in your mind as it stands now for market viability and application? Basically, how big do you have to be for this this type of project to be cost effective? And would underground geothermal systems ever be beneficial for individual homeowners? Will the cost ever match up?
Well, okay. I think, first of all, the air-to-air systems, right? And as I mentioned, I have relatives that have some of those systems and stuff. There's certainly a role for them, and the technology is getting better, right? They're getting better and they work well, so that there's certainly a role for that. And for individual homes or apartments or condominium units and stuff, an air-to-air heat pump system may be the preferable thing. I think that the geothermal systems that we're talking now, I also have a good friend that I work with a lot who has a geothermal system at his home. So they are applicable to their home. And I was just out there and he says it's worked extremely well. So it is applicable for individual units and individual homes as well. But I think
it's my son just put one in the suburb of Washington, D.C. And with the 30% tax credit, he was getting a fairly quick payback on the money.
Yeah. But I think that the geothermal systems, and particularly when you talk about these geothermal district systems and stuff, they're highly applicable for like individual buildings, right? So it doesn't necessarily have to be multiple buildings, although there's obviously advantages in multiple buildings, but it can be like an office building or a condominium complex, of multiple units in a building. So, and I know that Subterra has done quite a bit of that. If you look at their actual projects they've done, a lot of it has been with individual buildings, but with multiple units or multiple offices in it, where it's been where they're taking advantage of the larger demand and stuff. So I would say that you can't rule out geothermal. It all depends on the individual situation. So you can't rule it out for an individual home or unit, right? So that it can be applicable there.
Right.
But on the other hand, I think that where it seems to be most applicable is when you have multiple units and multiple buildings.
Yeah. McKenna, it might be useful after this call for you to send a notice to some of your members to see if they can identify potential opportunities. And this is if we could actually call and talk to them, you can get a fairly good idea initially over the phone and maybe exchange some information, whether it makes sense for a particular school or particular government building.
Yes, yeah. I think that as folks learn about this and as they either hear the recording or if you're attending this call now, if you're interested in following up with Gil and Jim and seeing what might be viable, we'll certainly put you in touch. Okay, question in the chat from Bill Webb. And if anyone else has final questions, please do put them in the chat. He says, is geothermal a good fit for upstream oil and gas industry? A big question there. And yeah, if you want to take a crack at it, otherwise might ask Gil to add more, or excuse me, Bill to add more context if he wishes.
Yeah, I don't know the answer to that, Gil.
Well, I mean, upstream meaning like refineries and other things, plants, processing plants, things like that. I think potentially, yeah. And I think that the idea also with the oil and gas industry, right? Since they're drilling, right? They're drilling wells and they're doing fracking and they're very active in underground drilling systems and stuff for their oil and gas industry, that there's obviously a potential relationship between that and putting in geothermal systems, both geothermal systems for their own plants, say for a chemical processing plant, or even for a refinery, you know, that it might be applicable. So yeah, I think there's certainly interesting potential there. Yeah, I would say.
And I see a comment here from Kelly Steele giving an example of geothermal for individual homeowners and advancing geothermal in that sense. Okay, and then Carl brings up an example of a potentially viable smaller project in Ronan, Montana. Good, so good things here. I think my last question for Jim and Gil as we close out this session is what's holding us back? I'm especially interested in the market landscape. I mean, Subterra is an example that was shared today, but one of my questions is how many Subterras are out there? And is that one of the barriers to why we don't see more broad popular adoption of geothermal, especially in Mountain West states?
Jim, I don't know, maybe that's something you could answer.
Yeah, well, just for Jackson, we do have, it's being promoted by Energy Conservation Works and so forth. I can actually find out a list of contractors there. I don't know if they work outside of Jackson, but we actually are making a fair amount of progress of having them installed in individual homes. So I can give that a list to you, McKenna, to see if any of them work outside of, the Jackson, Wyoming area.
Yeah, and again, I would go back to the point that I made earlier too, that there are, I'm sure in Jackson and probably in around here, I know there's other companies that are saying that they're experts or their experiences in geothermal. And I would say that what I learned from talking to the senior people from all these actual locations and sites where there's actually been a system built and stuff. What's extremely important is to really find a developer or a contractor that's actually had experience in building it and designing, building these systems, and not just that they're advertising that they know something about it, because it takes a degree of knowledge about the rock structures, the thermodynamic characteristics of the rocks and the aquifers underground, and how each design for the system is very unique, right? So it has to be designed specifically for that particular application.
Here we go. Now I'm unmuted. Great. Well, thank you again, Gil and Jim. That was an insightful presentation. It gave us a lot to chew on. So we're at the top of the hour. Thank you all for joining the Exploring Energy series. We are back on for December. Join us the first Wednesday of December. That's December 4th for the last Exploring Energy series of the year. And again, very grateful to Jim and Gil for being on the call with us. We will share their slide deck. They've given us approval to do that. And looks like we have a couple of folks who'd like to be in touch to dig into this deeper for some potential applications in Montana. So good things all around. Thank you so much.
Thank you so much too for having us. We appreciate it.
Yeah, thanks a lot.